Hello, friends. Today, we're going to be introducing a new kind of coordinate system. Um, if you think about the type of coordinate system that we have, we've got three dimensions, and each of the three dimensions is at a right angle to the other, right? So if you've got, I'm going to use this, this is very, very expensive, high-tech demonstration equipment. But if we've got two, right, so this is an XY axis, XY. These are at right angles to each other, right? Now, if I want to have a third dimension, that third dimension has to be at a right angle to both of those other things, right? So if I can do this, so here I have an X, Y, and Z axis. And I can call this a right-handed coordinate system because the way this works is I put my hand in the direction of the X coordinate, and then I turn my hand in the direction of the Y coordinate and my thumb. Anyway, you don't need to know this, but it's just that there are three dimensions and they are at right angles to each other. There are other types of coordinate systems, and we're going to look at one today. Today, we're going to look at polar coordinates. Okay, so just like on a plane, given any two X and Y coordinates, rectangular coordinates, you can locate a point. Well, that also works when we're dealing with circles. You think about it, all you have to do is have a given. So you start with an origin. There's got to be an origin in any type of system. And so what you can do is you can move any distance away from the origin along the x-axis, and then move some angle away from that. And then we've got angles that can go all the way around. So any point can be described by a radius and an angle. Right? This is two dimension. There are actually two different ways of getting the third dimension, but we're not going there. Right? We'll explain that to you when you're older. This right now is just a radius and an angle to give you any point on this plane. Okay, and we can represent this point a bunch of different ways. So let's take a look. Here's an example. It says plot and label the following polar coordinates on the polar coordinate grid above. So let's take a look at the grid and just see what is going on here. First of all, notice that we've got radius lengths. So we can go at 1, 2, 3, and those radius lengths are the same on the vertical axis as well. But again, these are not two different dimensions. This is actually the same dimension going out this way. And then the second dimension is going around. Another thing to notice here is that the radius and the circumference, which is described by the angle, they're always at right angles to each other. All of these radii are like spokes in a wheel, and they're at a right angle at the point where they hit the curve on the outside. So let's see, 2 comma pi over 3. So the way this works, so I'm going to go out 2, and I'm going to go around pi over 3. And so my first point is going to be here, 2 comma pi over 3. That's A. All right, the next one, 1 comma 3 pi over 2. So if I go out to 1, and then 3 pi over 2, where is that? um, well, 2 pi over 2 is over here, right? Because that would just be pi. So 3 pi over 2 would be over here. And so this is going to be point B. Point C is 3 comma 4 pi over 3. So I go out to 3. And now I need to go 4 pi over 3 around. And so that's going to take me over to here. Right? This angle here is 3 or 4 pi over 3. So this is C. And then D, 2 comma negative pi over 6. Negative pi over 6 is going this way, going clockwise, and the radius is 2. So I'm going here out to 2. And so now I'm going to label this as point D. Okay. Now, here's another one. Plot and label the following polar coordinates on the polar coordinate grid above. So let's take a look at this one. 2 comma pi over 4. All right, so I go out to 2, and I go around to pi over 4, so it's going to be right there. So that's point A. Now 2 comma negative 7 pi over 4. That's interesting. So 2 and then negative 7 pi over 4. That's almost all the way around the circle, right? But in the negative direction. So I'm going all the way around. So this is negative pi. This would be negative, negative 5 pi over 4, negative 6 pi over 4, which, the same. So it would be here. So it's going to be in the same place. So this is both A and B. Notice, same point, labeled in two different ways because of how we wrote the angle. The radius has to be the same. Now, C and 9 pi over 4. What does 9 pi over 4 mean? Well, 8 pi over 4 is just 2 pi. So it's pi over 4 past a full 360 degrees, past a full 2 pi revolution. And again, it gives me the same point. So it's A, it's B, it's C. Let's see if we can get 4 for 4. I don't know. We're going to try, but you never know. So we're at negative 2. Negative 2, how does that work? Well, we can think of this a couple of ways. We can go over to 5 pi over 4. So we can go to 2, and 5 pi over 4 would put us over here, but it's negative 2, so then we flip to the other side, and that gets us there. Or we start at negative 2, and then we go 5 pi over 4 from that. We kind of measure the angle from over here, from the negative axis. Either way, it does get us back to that same point. Same point written four different ways. So because of the cyclical or the periodic nature of these angles and the way that they work, there's an infinite number of ways that you could write a polar coordinate, right? So they want us to plot the polar coordinate 3 comma 5 pi over 6, and then to write those polar coordinates in two different ways. All right, so let's find out where we are. I'm going to go to 3 and then 5 pi over 6. That's going to take, it's not 6 pi over 6, it's one less than that. So I'm going to be over here. Okay, so here's our point, 3 comma 5 pi over 6. And then we're going to write this a couple different ways. One thing we could do, let's get a little creative here. So let's go to negative pi over 6. I'm going to give this angle negative pi over 6, and then negative 3. So 3, like to go over to the other side. So this could be negative 3 comma negative pi over 6. I could also think of it this way, that if I use the negative angle, I can go from here all the way around, and that would be an angle of 7 pi over 6, right? I'm pi over 6 past pi, so that would be 7 pi. And I'm not using a negative r, so it would just be 3 comma 7 pi, negative 7 pi over 6. So those are two different ways, again, infinite many ways of writing that. So because of the work that we've done with the unit circle, etc., we can relate rectangular coordinates to polar coordinates. Okay, and so if we have any point here, this is rectangular coordinates. You go over x, up y, etc. Polar coordinates, a r is the the radius, the distance away, and you've got theta, and then we can connect the two of them, right? Notice that when we do this, we get a right triangle, similar to the way that we've done all kinds of other things. This is actually kind of going back a little bit to what probably how you originally learned sine, cosine, and tangent. So let's take a look. Using trigonometry, we know that cosine of theta is x over r, and sine is y over r, right? Opposite over hypotenuse. And then we end up with these two identities, that x equals r cosine theta and y equals r sine theta. If you're in a physics class, you've probably seen this, right? Or like an honors, a higher level physics class, where we're constantly finding x coordinates and y, or like x components and y components, splitting all that stuff up. If you're not in a physics class yet, you're probably going to see this kind of thing getting into two-dimensional analysis. So now what they want us to do is convert the following points from polar coordinates to regular coordinates, rectangular coordinates, not regular. So what I would recommend doing is drawing, just so you can kind of get a visual on what this is and where this is. So 2 comma pi, so this just means we have a radius of 2, and we're going around pi over to here. So this is 2 comma pi. Right. Well, we don't really need to do a lot of work for this. We know that the coordinates here are -2, 0. Okay, but let's play along. So what I'm going to do is I'm going to take 2 cosine of pi to sine of pi. Okay, now I know that cosine of pi is -1, so that gives me the -2. And then I know that sine of pi, because I have the unit circle memorized, sine of pi is 0. So it's just 0. Okay, so let's take a look at B. 4 comma 5 pi over 3. Drawing this quickly, 5 pi over 3, that's almost 2 pi, right? It's down over here, and I have a radius of 4. So I'm expecting to get a negative y coordinate and um, a positive x coordinate. And so I can do this. Well, let's go back to blue for this. 4 cosine of 5 pi over 3, comma, 4 sine of 5 pi over 3. Okay, now what is cosine of 5 pi over 3? It's 1/2. So this is half of 4 is 2. And then sine of 5 pi over 3 is √3 over 2. Well, 4 times √3 over 2 is going to be 2 times √3, and I have a negative coordinate because I'm um, below the x-axis, you could say. And so let's take a look at the last one. Again, -3 comma 7 pi over 6. What's that? Right. So let's go to 7 pi over 6. That means that we have gone over to here, right? Pi over 6 past pi, but it's negative. And so we're going back over to this side. And so I'm expecting to be in the first quadrant, positive x, positive y. So let's start working with that. So -3 cosine of 7 pi over 6 and -3 sine of 7 pi over 6. Okay, so uh, cosine, let's do this one at a time here. Cosine of 7 pi over 6. Again, since that's over here, that's going to end up being negative √3 over 2. So let's see, -3 times negative √3 over 2. And then -3 times sine of 7 pi over 6 over here again. So this is going to be -1/2. Right? That's how far down we are over here. So -3 times -1/2. And so what I end up with is negative, or rather positive root, oh, try this again, positive 3 √3 over 2, comma, 1/2. And I don't really have to put the positive there. I can just leave that, but I do want to keep the 3. It was accidental. That's the solution there. Then using the Pythagorean theorem, we can go backwards. If we know the polar coordinates, we can use inverse tangent, or just solving for tangent, right? Inverse tangent has a restricted range, so we don't necessarily want to use that. But we're going to solve for tangent. We can use Pythagorean theorem to find r. So tangent will give us the angle, and then Pythagorean theorem will give us the r, the radius. And so let's see. So -2, comma 2. Okay. So this one probably could think about this one and do it -2, comma 2. So that's over here. I mean, that looks like it's along the 45-degree angle. So, but I don't know off the top of my head what the what the radius is going to be. But here's what we can do. We can take, so tangent of theta. I'll go back to blue for this. Tangent of theta is, so again, the y over the x. So it's going to be 2 over -2. And I'm solving for theta. And so what's the angle? What are the coordinates that give me 2 over -2? Well, that comes from, uh, so what I have here is like -1, right? And so that's when I'm going to have root 2 over 2 over negative root 2 over 2. And so that's where the sine over cosine. So the negative 2's cancel, it ends up being 1. So these are equivalent to each other here. The coordinate then, or the angle that I'm dealing with, is 3 pi over 4. Okay, so theta is 3 pi over 4. If I'm in the second quadrant, sorry, if I'm in the fourth quadrant, that also gives me a negative on tangent. But the thing is, I know that this coordinate, I know this is where this should be. Now let's use Pythagorean theorem. So 2 squared plus 2 squared equals c squared, right? A squared plus b squared equals c squared. And so it's 4 plus 4 is 8. So the square root of 8 equals c. So that's 2 root 2 equals c. Okay, and so I would write the coordinates as 2 root 2 comma 3 pi over 4. Those are the polar coordinates of that point. Okay, next one. Again, I'm going to draw this just to get a visual on where I'm supposed to be. So 1 comma negative root 3, that's going to be down here somewhere, right? So since I'm going over 1 and down root 3, yeah. Okay, so I'm farther to the right, or no, sorry, I'm farther down than I am to the right. So it's going to be over in this region. And let's see what we can get. So we know that tangent of theta is going to be, again, the sine over cosine. So negative root 3 over 1, which is negative root 3. Which set of coordinates gives me negative root 3? That's for when I'm here. And so in the standard unit circle, this would be root 3 over 2, comma, that would be the y coordinate. So it would be 1/2, comma, root 3 over 2. Put that back in there. Okay, and so what's this angle? This angle is pi. So for 5 pi over 3, that's the angle that gets me at that point, 5 pi over 3. Now let's take a look at the Pythagorean theorem. So 1 squared plus negative root 3 squared equals c squared. So this is 1 plus 3 equals c squared. And so 2 is equal to c. So the coordinates are 2 comma 5 pi over 3. On to c. This one, we don't really need to use tangent. We can kind of figure out where this is. We're down here at 0 comma negative 5. So that means the theta is going to be 3 pi over 2. And the radius is obviously 5. But let's just try this out, see what happens. So tangent of theta equals, so this is sine over cosine. So it's the y over the x equals negative 5 over 0, and everything explodes because I put a 0 in the denominator. So what it means is simply that it's undefined. Well, what's the place where, what are the angles where tangent is undefined? That's it, pi over 2, 3 pi over 2, etc. So that gets me the right angle. And then Pythagorean theorem, 0 squared plus 5 squared equals c squared. We end up with this, that c equals 5. So that's going back and forth from rectangular to polar coordinates. We can do it either way, all making use of trigonometry, sine, cosine, tangent, and the Pythagorean theorem. Polar coordinates also relate to complex numbers. And it says previously we've written complex numbers. I don't think we've covered complex numbers in this course. Perhaps theoretically you've done this in Algebra 2 or some other place. But the whole idea is that there's the real axis and the imaginary axis. And so any point on the complex number plane can be written as a plus bi, where a is the coordinate on the horizontal and b is the coordinate on the vertical, because it's the vertical times I. I is the square root of -1. It's the imaginary number. you have to leave these two terms separate, a and bi, but it's a way um, of plotting on the complex plane. So there's an example here. The complex number 3 plus 2i is represented as the point 3 comma 2 in a rectangular coordinate system. Right? We can also express a complex number in the polar coordinate system. Okay, so for example, when the complex number has polar coordinates r theta, then it can be expressed as r cosine theta and plus I r sine theta. Right? Again, the the r sine theta gives us the vertical. That's equal to y, right? And then r cosine theta gives us the horizontal. That's equal to x. So it says a complex number is represented by the point in the complex plane. The complex number has the rectangular coordinates -2 comma -2. What is one way to express the complex number using polar coordinates r comma theta? So let's take a look. Can we find r theta? So this is just like what we were doing before. We're just going backwards to try to find um, the r and the theta. Okay, so um, if it's -2 comma -2, then I know I'm going to be down over here. Okay, so let's do this and find out where we are. So if we say tangent of theta equals -2 over -2, that ends up being that tangent of theta is 1. Now, because of the way that tangent works, we could be at either um, pi over 4 or 5 pi over 4. But because we know where we're supposed to be, we're going to be in 5 pi over 4. That gets us to -2, -2. If it was pi over 4, then we'd be in the wrong quadrant. So theta here is 5 pi over 4. And then 2 squared, -2 squared, plus -2 squared. Applying the Pythagorean theorem now, r equals r squared. I said c squared before because that's the normal form of the Pythagorean theorem. A squared plus b squared equals c squared. But now I've grown up a little bit, and so we're going to call it r. And we end up with the same thing we had before. So r is 2 root 2. Was also we had square root of 8 is another possibility. So we can write this as r as 2 root 2. These are polar coordinates, comma, 5 pi over 4. That gives us that same point as -2 comma -2. For example 7, they give us polar coordinates to express this the complex number. So going back to example 6, we can rewrite this way as 2 root 2 cosine of 5 pi over 4 plus I times 2 root 2 times sine of 5 pi over 4. All right. But anyway, going back to example 7 now, what we can do is we evaluate this and we find what these coordinates are. So 4 times cosine of 7 pi over 6. Can I draw this? 7 pi over 6 is going to be over here. I know that cosine of 7 pi over 6, so it's negative. It's going to be negative root 3 over 2. So this is 4 times negative root 3 over 2 plus I'm going to evaluate this. So 4 times, and then sine of 7 pi over 6 is negative 1/2. So this ends up 4 times negative root 3 over 2. This is negative 2 root 3 minus I times 2, or 2i. And so the coordinates are negative 2 root 3, comma, -2. Those are the xy rectangular coordinates for that point in the xy plane as expressed in polar coordinates. And that is it for the notes on topic 313. Thanks for watching. Don't forget to like and subscribe.